Great, thank you very much. And I'd like to start by saying what a good set of presentations there've been this morning. Really enlightening and a lot of synergy between them. And I'm going to kind of turn that on its head a little bit. So I come not from the digital twin background, but I come from the problem space. And I'm, along with colleagues, finding our way into the digital twin solution of that. And at least that's what I thought. And then I started to reflect on my career, and I realized that I'd been working in digital twins for the last 15 years, and but they weren't called digital twins. So things like supply chain execution systems are digital twins of the supply chain. Things like fly-by-wire in aircraft, when I was an aerospace engineer, they're actually to do with controlling of an asset in a digital twin way. But I'm going to start by really framing the problem we've got in decarbonising transport. So I'm a professor of logistics and sustainability at Heriot-Watt University. My team have been building digital models of the transport system for the last 12 years. And transit represents a transition from digital models into that digital twin space where we're looking for sort of real time or right time control aspects. So let's start with the problem. And some of you may not have seen this because you're not from the same problem space. This graph really refers to something called the carbon budget. And the carbon budget is how much carbon we can afford to emit before we reach a tipping point, beyond which we cannot return to the situation as it was before. And the other side of the tipping point is not a good place to be. That's where we've got floods, severe weather events, and spiraling feedback loops that make the situation a lot worse. And based on current emission levels, so that's the emission levels as they are now, we have about 5 years before we exhaust the carbon budget and go past the tipping point. And that's quite frightening because the amount of change that we've got to deliver in that period of time is massive. It's even recognised by the government. You know, we talk a lot about net zero by 2050, and the implication is that it's sort of a linear journey from where we are now to 2050, but it's not. We have other targets. So by 2030, we're expected to achieve a 68% reduction. And by 2035 or so, a 78% reduction in carbon emissions. The reason this is all important is that transport represents 30% of the carbon emissions worldwide. The next thing to think about in this problem space is it's very diverse, and it's something that every person in the country touches every single day, whether it's directly by getting on a bus or in a car or walking or getting on a bike, or because you sat at home working from home and you're getting your Amazon deliveries or your food deliveries or whatever it is, or even just your post. So every single person touches transport every single day. It's diverse because it covers 4 modes: air, maritime, road and rail. 5th mode, active transport. It's the range of assets that are deployed in the transport system is huge. 38 million cars, 35,000 buses, 500,000 HGVs, and that's just the road transport element. And they all operate across a shared infrastructure. So transport isn't about a car journey or a bus journey. It's about how people and freight move around the country, very often across modes. So, a journey for a piece of freight that lands in Dover might involve a road journey to Daventry, where it's unloaded, put in a warehouse, then goes on a container to by train up to Glasgow, where it's unloaded and finds its way into a supermarket, possibly to home delivery using a small electric vehicle van. The other thing that's worth noting about the transport system is its economic significance. The one thing that we discovered during COVID is that whilst people could largely be restricted in their movement to local areas or journeys that had to be made by necessity, freight can't. Freight has to keep moving. It's how we get food in the supermarket, it's how we get food on the plate, ultimately. So freight is a very important economic element. The whole transport system is populated by a large population of individual companies or individuals with a very light touch regulation. Now, what this graph shows you now is the flow of money into decarbonising everything, but transport is in the bottom right-hand corner. And the money flows from left to right. And without going through this step by step, broadly speaking, the pale blue flows are from government, and the orange stroke red, I say orange stroke red because I'm colourblind and it doesn't mean anything to me, but I think it's orange stroke red. The orange stroke red flows are from private finance. And that is what is mostly flowing into transport. And that's because most of the transport operators, the asset owners, are private companies or private individuals, all operating in their own interest. So we have this self-organizing system, which is complex because they're all making their own decisions, partly based on what they see around them, the decisions made by other actors in the system, or some other thing. So, last thing I want to say, well, not quite the last thing actually, but another dimension to this is the pressure of time. So, this graphic shows two panels. On the left, there are two bands, and the top band shows the impact on inflation if we start decarbonising now, well, in 2022. And the bottom band, the sort of the pale blue again, shows the impact on GDP. So inflation will go up because decarbonisation is expensive. And because decarbonisation is expensive, we take resources away from productivity. GDP will go down because same reason that we're taking money away from productivity. And we have a short period of time in which to recover that expense by increasing the prices of the products or services that we sell. The panel on the right shows what happens if you delay by 4 years, just 4 years. And so you see inflation more or less triples, and GDP loss or decrease more or less does the same thing, triples as well. The last element that makes this complex adaptive system that we call the transport system complex is that it is tightly coupled. As we move increasingly to electric vehicles, I could have picked another transport mode and said hydrogen or whatever, but if we stick with road for the moment, as we move increasingly to electric vehicles, the supply of that electricity, and this is something that was touched on by Simon in the virtual energy system, will become scarce. And when you have a scarce resource, you have tight coupling. That tight coupling means that any changes to the system cascade quickly through it and cause this sort of dynamic wave of disruption. So ultimately, we've got a tightly coupled, complex, adaptive system that has to transition from where it is now to some future state which is radically different to where it is now in a very short period of time. And that's the problem. Okay, I haven't talked about digital twins yet. The reason that digital twins is important in this discussion is that length of time we've got to adapt. We don't have the time to try out in the real world all the options, rule them out, modify them, try something else, because that's going to take too long. So the only way that we can get to a design for the future transport system is by looking at it digitally. Okay, so that's the digital modeling component. The second thing that we need to do is recognize that this is going to cost a lot of money. That graphic showed that, I didn't mention it, but the graphic on the flow of cash into decarbonising transport shows that currently we spend $170 billion a year worldwide on decarbonising transport. And that's what we spend now. That will quadruple quite easily with time. So it's going to be expensive. And that means that we've got to manage the transition from where we are now to this future state by concentrating on resource efficiency. So that's an efficiency argument. And the third thing that we need to recognize in this complex adaptive system is that when we get to this future state, it will be very different. So the planning of transport operations will have to respect different constraints. For instance, an electric truck is going to be able to carry less because it's carrying a big battery around with it. It is going to require charging, which will take half an hour instead of 5 minutes at the petrol station. And all of that will mean that we have to reorganize the way we do transport. It's not the assets, but how we do transport will have to change radically. So there's an optimization piece in the future state, which we've got to in the current version of transport through a process of evolution over decades. What we're talking about is that within a single decade, the next version of the transport system will have to be optimized, or it will be very expensive. So we've got design a future system that doesn't exist. That's a digital modeling piece. We've got an optimization of the transition, making sure that we do that at minimal cost. That's an optimization problem. And then we've got an optimization of the end state, which in an ideal world would be based on the optimization capability that we developed for the transition. And that is another optimization problem. So we've got a problem space that is defined by a need to act fast, which compels us to look at digital approaches, and then a need to optimize both the transition, the change, and the end state. So what is transit? Transit is a big project. It's split into two phases. The first phase was consultation, and the second phase is actually to do with implementation. It's looking at the decarbonisation of all transport modes, so all 5 modes are included in it on a national basis, and it's focused on the appropriateness of the digital twinning process to do that. So in the first phase of transit, we did this consultation, and over 400 organisations and individuals were consulted, and we found that the biggest barrier to the transition, in other words, people investing money in things that will change the transport system and decarbonise it, was risk and uncertainty. So the question that spins out of that is how do we reduce uncertainty using digital twinning? The second thing that came out of it was the need, and other speakers have touched on this today, the need to include human behaviour in that digital twinning process? How do we incorporate humans in the loop dynamically so that we can capture their behavior and their decisions and their choices and modify them as they respond to a perpetually changing environment as defined by the transition? And the third biggest concern that came out of the consultation was data sensing systems and Internet of Things. So together with the problem space and the consultation, we can frame a piece of work that is going to try and address the challenge of decarbonising transport over the next 5 years. That's the second phase of transit. It's got £19.5 million of funding assigned against it. And we've also raised industry contributions of about 22 million. So it's a significant amount of money. We recognise that we will not do this alone. We will have to work with others, and I'll come to speak about that in a minute. So it's being led by myself, and my co-investigator or co-leader is Professor David Flynn at Glasgow University. He really does come from the digital twinning stable. So between us, we've got the problem space and the digital twinning aspects of this covered. We recognise that there's great independency between the modes. So what we do on road will affect how much moves by rail. What we do in the ports will determine how much flows by aviation. And we recognise that the bit that sort of keeps all these modes connected is policy. And we also recognise that in designing this future system, we have to ensure that nobody is left behind, so that we have equity and inclusion. We have to recognise that the biggest challenge is changing human behaviour, not delivering electric vehicles, because we built those, we know what they are, and we know how to charge them. From a digital twinning perspective, we recognise the problems that other speakers have talked about today, which is architecture, ontology, cybersecurity, data security, and interoperability. We are part of a trio of investments being made by the UK research councils. Transit is the biggest investment, I think, at 20 million. DARE is a project that I'm also involved with and is worth mentioning today, which is looking at resilient transport infrastructure. And that's being run by Newcastle and the other partners are Cambridge and Glasgow again. And then there's Ensign, which is looking at the energy transition. So we will work closely with these other projects, but also the broader digital twinning community, some of which have spoken today. We need to engage with them and make sure that we are leveraging the work that's already been done in order to achieve this big challenge of decarbonising transport. In terms of the way that we're organised, we've looked at the different modes. We will develop digital twins in each of those modes. We will then work on federating them, bringing them together in different levels of federation. So we put a layered approach to this to minimise the risk. And we aim to have a federated system of systems digital twin in 5 years' time. We've focused on use cases, and the use cases are Port of Dover, connecting to the West Midlands via Daventry, which is a logistics hub, biggest logistics hub in the country. West Midlands for the mobility of people in and around the West Midlands area and the connected spaces for mass transit. East Midlands Airport, because that is a hub for parcel deliveries and air freight. And we will look at the connection, onward connection from that parcel delivery hub into West Midlands for final mile delivery services. We've got 7 universities involved in the project in total. So it's being led by Glasgow and Heriot-Watt, University of Leeds, who have a strong transport pedigree, Cranfield University, who have a strong digital twin and transport pedigree, Rail, who already have a digital twin for the rail network at Birmingham. Maritime is going to be led by UCL, who have great domain knowledge in maritime. So, in conclusion, with the problem space is emergent. We don't have a future transport system, a physical entity that we are trying to twin with. We have to, first of all, design it. It is complicated because it is a complex adaptive system, meaning that it is self-organizing, very dynamic, changing all the time. Whatever we do tomorrow will impact the possibilities for the day after and the day after that. It is tightly coupled, so small changes can have big effects in the system. And crucially, it's emergent and not linear. And that's a paradigm shift because a complex adaptive system cannot be controlled. You can merely interact with it. The analogy I use, it's like steering a ship in a storm. You have to do something, otherwise you're the victim of the storm. But what you do won't necessarily result in what you wanted it to do. So you're constantly engaging and steering the ship. And that's really the case for digital twinning, I think. It is a paradigm shift. And we're considering this as a socio-economic and technical problem. So it's got 3 dimensions that we have to work across. And it presents a unique problem, which is how will we share the benefits and costs of the whole system optimization? When we change something in the whole system, which might mean a bus operator not operating some routes because they can be done by rail, then we're asking that bus operator to make a sacrifice to benefit its competitor, the train operator. So how do we incentivize that and make sure that it's fair and equitable? Climate change dictates that we urgently design this future system. We have to remove uncertainty. In doing so, we will reduce investment risk. And if we reduce investment risk, there's £8 trillion available for investment from the private sector. If we don't reduce risk and uncertainty, it will continue to be invested in those things that are less risky, which at the moment are the dirty industries. And to minimize the overall cost of this, we have to optimize resource efficiency, and that is the digital twinning challenge. So slightly different take on digital twinning coming from the problem space, but I hope it was interesting, and we're open to engagement, as other speakers have said today, with the whole community, and indeed some of those discussions have already started. Finally, the clock is ticking.
The clock is ticking.
In many ways, I suspect.
In so many ways, you're right, Phil. Thank you very much indeed, and I think it was actually very timely for you to kind of change the angle, change the perspective. That was really helpful, and I think coming at it from the point of view of a problem, not just any old problem, but like one of the biggest problems, and one that absolutely must be solved. I think that is that kind of really puts everything into focus. And I think your point on risk is super well made. I mean, it's a funny thing, isn't it, where people invest in something that looks less risky, but actually that very investment is of a greater risk to humanity. I mean, there's a big old irony going on in there. So Phil, that was brilliant. You've made us think, and I think also what you've done is kind of very well articulated why we have to do this stuff. And the three previous speakers are kind of indicating what's going on. And I think you kind of hit the why drum very well. So let's take a few questions. And we've only got time for a few because we're going to move into a panel. But thankfully, Phil is staying for the panel, so we can kind of carry on the conversation. And the first person that I'd go to, I'm afraid I don't know their name. It's BM. If I unmute you, would you like to ask your question? So hopefully, there you go. Do you want to unmute and ask your question?
Hello.
Yes, hi there.
Can you hear me? Thank you for giving me opportunity to ask a question. I thank you for your interesting presentation, Professor. And I have one question regarding your presentation. So that you mentioned about the needs of digital models or digital twins for transportation sector. So I wonder what can you at the end of your presentation you mentioned that digital twins or these digital models can be used for transition costs. So what will be the other examples that digital models or these digital twins can help rather than using the existing traditional softwares? What will be the difference and benefits?
Right. Okay. So the big challenge here is that the radical change that we're talking about. So a number of things are changing at the same time. So the energy input to the transport system will change at the same time as the technology in the assets, so that in the trucks and the buses and the cars will change. And the infrastructure will change indeed. And there are infrastructure changes, options that we need to consider. So if I take an example of the electric road system versus static battery chargers. So the electric road system is where you put cables above the road, so that vehicles, heavy goods vehicles mainly, can connect to it and do charging on the go. And that is a very real alternative that requires massive investment on the scale of HS2, so 20 billion pounds or so of investment. But operationally, the benefit is that your logistics vehicles don't have to stop for 30 minutes to charge. They're charging as they move up and down the motorway. The impact of that is that the charging is delivered from the energy system is dynamic. It's 150 kilowatts instead of 500 kilowatt power for a static charger. It means that the vehicles arrive at service stations fully charged and don't need charging facilities at the service station. So I guess the point of that is that the traditional models have tended to think in silos, and what we need is a new digital capability that breaks down those silos and goes across different modes and includes energy and infrastructure. And that's probably the difference.
Yeah, okay, thank you. So I understand that the advantage of using these digital models will be interconnectivity, connecting
Yes.
one sector with another sector and see potential synergy, and
Yes.
that where the value come from. Yeah, is that right?
And you raise an interesting point, and I should have said our approach to developing this model or this digital twin is through federation.